Thank you, Thomas, for introduction. Thanks for inviting me here to give this talk. So I will talk about some recent results about attacks on the McEliece cryptosystem. So this is joint work with several people. So Magali is involved in this. Alain Couvreur is involved in this, and also, very importantly, a very brilliant PhD student, actually, which is instrumental in many of these results, which is Rocco Mora. And so this has been results obtained this year and the end of last year. So, but again, what is the McEliece cryptosystem? I'm going to record it in a few words. So you start with a code, so a linear space over some finite field, FQ, of some dimension, and what you can for which you have an efficient decoding algorithm. And McEliece used binary Gopa codes, and it was a very good choice. Probably, with hindsight, it was an excellent choice. So, if you want to specify a code, you have many ways to specify it. You can specify it, if it's a vector space, just by giving a basis of it. This is the generator matrix here, G. And so whose rows are just actually the basis element of a subspace. And so what you do for encrypting it, you take a linear combination, which is the message of these vector elements. So you multiply the M here by this matrix G, gives you a code word, so an element of a code space, and you add an error of some Hamming weight T, for which you are able to decode with a secret structure. Here for the Gopa code, the matrix is not enough actually to decode it, but there is a hidden polynomial structure which allows you to solve the problem. If I give you this noisy code word here, Y, which is the sum of a code word here plus some error E, you can find back actually the M times G and then the M you started with. This is a decoding problem, and you have something very efficient to do this. So it's just this, actually, this McEliece cryptosystem. And it's one of the main advantages of this cryptosystem is it's the oldest public key cryptosystem which has not been broken, either by a classical computer or a quantum computer, really. So 55 years of research have not changed much the picture. Right now, the best attacks on this scheme boil down to the fact to solve a decoding problem where I give you a linear code, so they give you this generator matrix, and you want to solve a problem if you have, a noisy code word here. You want to find back actually the code word we started with. So the best argument for doing this are basically exponential in T. And what is also very nice about this, it's actually this exponent that you have here in T has not changed much over the years. It's basically almost constant between 62, where there is the first non-trivial argument which has been found, and now. So it's a very stable system somehow. If you want to break this scheme, actually, if you want directly to find, solve the decoding problem, it seems a very hard problem. Of course, there's also a drawback here because the public key here is large because it's a matrix we started with. And so you should really think of, you have sizes of matrices of several thousands, so it makes actually big public keys. And you can say, okay, but wait a second, you started, it's not, you know, you did not take any linear code to do this, you chose a Gopa code, which has a polynomial structure. Maybe there is a way to recover from the generator matrix from a basis of the code. Actually, you can recover the hidden polynomial structure. Well, here this has not changed much over the years. Still, for a long time, more than 20 years actually, The best method here for doing this is just trying to enumerate not any GOPA code, but all GOPA polynomials. So there are more GOPA codes than GOPA polynomials, but you can enumerate GOPA code polynomials. And once you have a GOPA polynomial, oversimplifying a little bit, actually, if you want to find the GOPA code you started with, you have to solve an code equivalence problem. And for this, a very good algorithm doing this, polynomial time by Nicolas Cendrier. So the support splitting algorithm. But there is this combinatorial problem of enumerating this. And this enumeration of all GOPA polynomials is exponential here. And basically way bigger here than the exponent of message attacks. So this was a picture for many years. You are really, a case where key attacks, you can forget about them, and you really actually face the problem of decoding a generic linear code, and has not much it has been done for quite a long time. This situation has changed a slightly bit. In 2011, when with Fougère, Gauthier, Otmani, and Perret, we solved a slightly different problem, easier problem apparently, which is not to find the GOPA code itself from a generator matrix, but just trying to solve the problem of distinguishing if I have a generator matrix coming from, let's say, a random code, or a generator matrix coming from a GOPA code, can I distinguish in which case I am, random code or GOPA code? So this problem doesn't recover the algebraic structure itself of the code, but you just want to distinguish this thing. And, well, we tried actually to break the scheme, of course, but we did not succeed it because we found in this case a linear system for which we thought there were enough linear equations to solve it, but unfortunately the GOPA case, it turns out that the rank of the system was much lower than what we expected. However, the linear system that you get for a linear code, a generic linear code, actually has the right rank. So you have a way to distinguish a GOPA code from a random code by this kind of attack, which was not an attack, but it turns out to be a distinguisher, a GOPA code from a random code. However, this only worked in a very tiny regime. It really required here that the dimension of the code is really close actually to the code length. So it requires actually that code dimension here is of order square root of the length. So you're going to say, okay, is there at least one possible application of this kind of thing? Yes, there was at that time, because there was a signature scheme proposed in 2001 by Courtois, Fignas, and Cendrier, signature scheme based on GOPA codes, which were precisely in this regime. So there was not an attack on the scheme, but it was, we were actually, some distinguishing an attack. We were able to distinguish the code which is used in this scheme from a random code. Not an attack, but still something. At most of all, what is important here, it was polynomial, which is good. Because it was just, computing the rank of some matrix. So this was a situation for a long time. I couldn't believe, actually, that this distinguisher could not be changed into an attack. So it took a long time, actually, to be able to do this. So it took us more than 12 years, actually. But finally, we got something, but it did not work for GOPA codes. Okay, but what did we obtain? So what you should be aware of, there is a slightly more general family of code, which is called alternate codes, which basically have the polynomial structure of a GOPA code, or the polynomial structure of a GOPA code which allows you to decode. But the GOPA code is associated to some specific polynomial structure. And let's say the alternate code is a more broader family of polynomial code in some sense. What we are able to do is to turn this distinguisher into an attack, the beginning of this here, precisely in the regime of parameters for which actually the distinguisher applies. So in a very small parameter range. it turns out that it's going to work for binary codes. Unfortunately, it doesn't work if the alternate code is a GOPA code. There's a very bad thing happening in this case. In the particular case where the alternate code is a GOPA code, the attack doesn't work anymore. This would have given an attack on the Courtois-Finière-Cendrier scheme, but it didn't. But it's going to work. It's going to recover a polynomial structure. If you take a generic alternate code, it's going to work. So this was probably one of the first results of this year. And then what we managed to do with it, by a completely different tool, we managed to find a distinguisher which works for basically all GOPA codes and alternate codes of interest. So this is, I mean, the most important result is probably this one. So it works up to rate 2/3. So it really, you know, it's a way to distinguish the codes which are used in the classic McEliece cryptosystem right now from a random code. Well, there's a caveat here, okay? You're going to explain something in a few seconds, but still, potentially, it can do this. And without enumerating all GOPA polynomials, for instance. So it's a completely other way to doing this. So what we did here, we associated a space of quadratic forms to the code in a very natural way, and we looked for low-rank quadratic form in this space of matrices. And this gathers as distinguisher. We're working right now in characteristic 2, but this is not important. It's just to have an analysis what we have something working on from characteristic 2. It's certainly going to work also for other characteristics. And what is good, it generalized what we had before. So now it's going to work basically for any code regime here. It's going to be, polynomial in the old regime because it's the same distinguisher. In the old regime of parameters, it's basically the same distinguisher. But now you can go beyond. And what's also good, if you look at the regime, which is not interesting in practice, but still interesting for theoretical reasons, where the codimension here, it is n minus k, the difference between the length and the dimension of the code, is sublinear. So let's say n, the length here is some power of a codimension which is between 1 and 2. 2 corresponds actually to the old distinguisher regime. 1 actually corresponds to the linear regime. Well, it turns out that the distinguisher, the complexity of the distinguisher is better than message attacks. It's really better. So there's definitely something going on here. There is definitely an improvement, but it requires, you know, degenerate parameters. And so now you're going to say, OK, and what does it do for classic McEliece? Well, nothing. Essentially nothing, because it gives an attack, a distinguisher attack of unreasonable complexity, which is actually what you see here in the last column. So galactic complexity. But if you look at the old key attacks, also galactic complexity, but more galactic, sorry. Okay? So it does something. It really does something. And it's not the end of the story. And this new approach of looking at this quadratic form gave us also a completely different way of attacking the system. Well, we had this distinguisher, what in some very weird cases, we were able to transform it into an attack. And now, for all of a sudden, now we can attack all alternate codes where they are distinguishable with the old distinguisher. All of them. Not 2 or 3, actually, killed everything. So it just finishes this thing. And now we also have an attack which is working from some GOPA codes. Okay? Some for GOPA codes, but it requires that the degree of the GOPA polynomial is less than the field size over which a code is defined minus 1. So it doesn't affect here because the GOPA polynomial here is of degree, let's say, 50, 100, something like this. And so it really requires big field sizes to work with, so not binary for sure, but it does something for certain Gopa codes now. And the attack is polynomial. Okay, so this is actually basically gives you the picture what has been achieved actually this year in this field, and now I'm trying to explain how it was achieved. So first of all, now I'm really going to the details. I'm going to explain what an alternate code is, what a Gopa code is. But before this, I have to explain, I have to give a family of codes which is related to this, which are Reed-Solomon codes. So a Reed-Solomon code is a very simple code which has excellent error correction capabilities. And actually, it has also been proposed to be used in this McEliece setting, and of course, it has been broken. There's a Sedelnikov-Shestakov attack. But it's a code with excellent decoding properties. And it's a very simple structure. So what you take, it really needs a big field because you have to take n different elements in this field. N will be the length of the code, and the code itself, the code space, are just evaluation of polynomial up to some degree. If you want a code of dimension k, you go up to polynomials of degree k minus 1. Evaluation of this polynomial and the endpoints you have chosen. Px sub 1, Px sub 2, and so on. And you can generalize slightly this thing by multiplying each coordinate by some multiplier, which is y sub I here. So you multiply each coordinate by y sub 1, y sub 2, and so on. And y is called the multiplier, and x is called the support. So excellent code actually to decode. Unfortunately, if you use in the McEliece crypto system, if you give me generator matrix from this, I'm going to recover the x and y. It's all what I need actually to decode it with the Sedelnikov-Shestakov algorithm. So there was an attack in 1992 actually on this. So this doesn't work. However, Gopa codes are not like this. So they are going to hide a little bit of structure. And in more general, an alternate code is this. Gopa code has an additional structure. I'm going to talk about it in a few seconds. But an alternate code is how do you hide the structure in the following way. First of all, you choose the FQ where you want the Gopa code or the alternate code to live in, okay? Then you choose an extension field FQ to the M, over which you define the generalized Reed-Solomon code. And then what you do, you hide this generalized Solomon code by taking the subfield subcode of it. Meaning, what you do here, you just take here all the code words of a generalized Reed-Solomon code which belong, or for all host coordinates belong in the subfield. So these are linear code, again, it's easy to see. But it has, you know, one part of the polynomial structure which was used here has vanished. And if you want, of course, to have binary codes, this is the way you have to go because you don't have binary, non-trivial binary Reed-Solomon code, for instance. Just because of this constraint, actually, that the field size has to be bigger than the length of the code what you want to use. So code of length 2 is not very interesting. Okay? So this is actually how they are used. There's another important thing that I have to say, and you have to talk about the dual code. What's a dual code? I haven't, so it's a perpendicular here thing here, what I call here. It's just a set of code words, set of words in the space, which are orthogonal to all code words. So it's an orthogonal space here. The dimension is, of course, the length of the code n minus the dimension of the code. And it turns out that a generalized Reed-Solomon code, the dual, is also a generalized Reed-Solomon code, has the same structure somehow. And if I recover actually the dual code here, they have the dual here code has the same support as the code itself. So basically finding the polynomial structure of the dual code is the same as finding the polynomial structure here of the code itself. And so it's really what I'm going to do after. I'm really looking at the dual for certain reasons that I'm going to explain later on, which will be really apparent later on, but not right now. Okay, so this is now the picture. You have this code which has a polynomial structure which is hidden in a extension field, and you want to recover this polynomial structure in order to be able to decode. Okay. And now I'm going to give a key ingredient in this setting. It turns out that there was a very, very convenient tool to try to attack this system. And it uses a very peculiar property of generalized with Solomon code. And it uses, you know, an object, when you see it first time, you just think this is crazy, this is not going to work, it's not going to give you anything. But it was introduced by Wishbrink in 2010 for cryptonizing the Berger-Loydreau scheme based on subcode of generalized with Solomon codes, and it was a very powerful tool. So what is it? I'm going to, first of all, to define a product on vectors, which doesn't look interesting, but you see it first sight. It's a show product. You take two vectors, and you just multiply component-wise. Okay, why not? And then you could say, I'm going to define the component-wise product of two codes, just by taking, you know, all component-wise products of one element in the first code and one element in the second code. But this is not a vector space anymore. So in order to get a vector space, you just take the vector spanned by all these products. So why this thing should not be interesting? Because the dimension blows up quickly. Just because what you expect in things like this is this product here of two codes. The dimension should be basically probably the product of the dimension. It cannot be bigger than the code length, so it's the minimum of this product and the code length. So it should attain quickly, actually, the code length. If I start as a code, let's say, of rate 1/2, meaning that the dimension is half the length, actually I should get something which should be the whole space. Why is the product? Just because it's certainly generated by all products here on one element, one basis element of the first code and one basis element of the second code. It's a little bit smaller if you take the same code, A and B here, because A squared here, you use commutativity of this product, and so it's just generated by all products of the form A times A sub j here. A sub I are basis elements here, but you don't have actually to take both of them. So you gain a little bit, but not much. So this doesn't look good, does it? No. But what's going on for with Solomon code? With Solomon code, this actually the product doesn't behave, you know, in a normal way. Definitely not. Definitely not. It's just actually if you square generalize with Solomon code, the dimension is just twice the dimension minus 1. So where does it come from? Simple. It's just because the degree of a product of two polynomials is the sum of the degrees. It's just this. Why is this? Look. I take an element of the generalized with Solomon code here. I multiply it by another element of the generalized with Solomon code. So I get here the y sub I squared, of course, and then here I get a product of two polynomials whose degree is the sum of the degree of this polynomial and this polynomial. Okay? And so definitely here, it means that the whole thing that you see here lives in a smaller Reed-Solomon code. Not a bigger, I mean, not a small code, a slightly bigger Reed-Solomon code, whose dimension is the degree here of this maximum degree of this polynomial plus 1. So it gives you a 2k minus 1 here. So it's what it explains actually, but basically the dimension doubles instead of being squared. So kind of unusual. And actually, this explains the distinguisher that we found. Because this property somehow survives actually in the dual code. If you do here in the dual code and you take the square, there is a regime of parameters for which you see here, if you take a random code, of course it behaves in the usual way. So if the dimension of the code is r times m, here, what you expect is this dimension here. mr plus 1 choose 2 here, what is what's going to happen for a random code. However, if you take a Gopher code and Latin code, you subtract something to this. And this is basically coming from actually what happens from the generalized with Solomon code here, which is related, to which it is related. So there is something going on here, and this explains the distinguisher. It also explains why the distinguisher is not going to work for a big regime of parameters, because you want this quantity which is here not to be n, because n is what's going on actually for a random code. So you are in a regime parameter for which this quantity should be smaller than n. And so this explains basically that the m times r, which is the codimension of the code, is basically of the order of the square root of the length. So this really explains actually why we are stuck here at this regime actually for having a distinguisher. Okay, so this already explains something. And now I'm going to explain how we got an attack from this. This distinguisher can be transformed into an attack. So how does it work? It does something really weird. It considers a shortened code. So what is a shortened code? A shortened code is just a code where you put a 0 in in a certain number of positions. Instead of the code word which has 0 in certain position. And on this position, you just drop here the position. So it's a code of smaller dimension and smaller length also. So what you do here, you are going to take, so I'm going to do this with an alternate code, first of all, okay? Not a Gopher code. I'm going to be taking a slightly larger family of code, alternate code. And I'm doing this operation of shortening of the alternate code. So if I shorten the alternate code, what is good, in one position, is in more position, it still stays an alternate code, but of the same degree here. The R doesn't change. Too bad, but it has the same structure. I can shorten the dual of an alternate code. It's not a dual of an alternate code anymore. It's something real here, some kind real of structure, and I put it squared. And now what I say here, that the alternate code C that I have here multiplied by an alternate code of dimension 1 less, I don't know what it's going on at each time, is included in the square here of this weird code. It's here. Okay. So how do you use this? So you use this in the following way. If you assume here that this code, alternate code of degree r minus 1, is the biggest alternate code satisfying this property, so building that you have something like this happening, if A times a code that you know, X is a code that you don't know, is included in another linear code B here. If you want to find the biggest subspace which satisfies this property, you can find it easily, and you just actually have to solve a linear system. You see this directly, because what are you going to do? So you take an unknown code word in X here, so you just take the unknowns of the coordinates, and you are going to say multiply by any element, basis element of my code A, it should belong here to B. It's definitely a linear equation. And so you just solve the linear system and you get X. So if you have an equation of this kind here, and where X is the biggest code satisfying an equation like this, you can find it just by solving a linear system. And it turns out that actually the biggest subspace satisfying this property for an Artan code is this Artan code of degree r-1. When you take a generic Artan code, if you take a Gopa code, which is a particular Artan code, doesn't work anymore. You have something bigger, unfortunately. So it's why actually the attack, what you are mentioning, it doesn't work, but it works for Artan codes. Because now we have a way to decrease by 1 the degree of the Artan code. Okay, so you can decrease by 1, and then there's a condition for which this holds actually, which I haven't talked about, which is this condition which R should be bigger than Q plus 1. The degree of Artan code should be bigger than Q plus 1. So you can go up to degree Q here. And so after this, there is a way, if a degree is small enough, actually we can use Grobner basis techniques to recover the X and Y. Okay, so basically this solves the problem. So we have a way to decrease the degree just by solving linear systems. And then actually at the end of the day, we just have actually to solve an algebraic modeling, Grobner basis. It turns out it's polynomial in this case. So there is an efficient attack as soon as Q here, or Q plus 1, can be equal to 3, which is actually the case for 2 and 3. So it works actually for Artan codes of degree 2, Artan codes of degree 3, and doesn't work above. So we have something which is close to attack the binary Gopa codes which are used actually in the CFS scheme, so Courtois, Vignas, and Cendrier. Doesn't work right now because they use binary Gopa codes, and binary Gopa codes, for some odd reason, actually this doesn't work because the code that we get in this case by solving this linear system is just too big. It's not an Artan code of degree 1 minus 1. Okay, can I give you an intuition why actually shortening does something here in this polynomial thing? I'm going to explain it for generalized with Solomon code. Look, if I take a generalized with Solomon code, and what I do, I just drop one position. Why not? Can do this. And then I take the shortened Reed Solomon code. So Reed Solomon code shortened one position, X, let's say it's in position I. Shortening means that the code word has to be 0 at this position. But remember, the code word, the coordinate at this position is an evaluation of a polynomial, evaluated at x sub I. So if it's 0, it should be a polynomial which has the root x sub I. So it means actually that the polynomial I'm after, they have here, as you see here, as a root x sub I. And if I put them squared, actually I get polynomials which have actually a 0 of order 2 at x sub I. And now if you want to solve here c times x, is equal to d here, which is at the bottom, well, you have to get c inside are just a standard polynomial. Indeed, you have polynomials at, we have a 0 of degree 2, of order 2 here. And so you have to multiply here. X should be formed by actually evaluation of polynomials which have a 0 of order 2 at x sub I. And just because of this, it's easy to see. So x has this property here, because formed by polynomials of degree 2 here, which have a 0 of order 2 here at x sub I. And just because of this, and you look at the dimension of the thing here, you see that you have a generalized with Solomon code of order k minus 2. So you'd have a drop of 2 in the dimension. So this looks good. It's a good operation. So for with Solomon code, just because of this thing about the zeros, you can drop the degree here, the polynomials which are after, by 2. So just one that we have in our case, the subcode case, but still is something. So this is basically what really explains somehow what's going on here, why we shortening actually does something in this case. And I'm going to talk about the new tool. The new tool, quadratic forms. So how do they come from? Why do I want to have quadratic forms? So first of all, there is one very simple thing, very simple. I'm going to explain why I'm going to do a very simple operation which is going to do something non-trivial. I'm going to take my code here, my dual code of my GOPA code of Atom code I'm interested in. Well, this code lives over FQ. It's unable to see the X subice and Y subice which belongs to extension field. No way. They live in FQ. My X subice and Y subice will live in FQ to the M. But what can I do here? I can just lift my code actually in the higher field. There is a trivial way of doing this. I take my basis element and I just take linear combination over FQ to the M. So this gives me a FQ to the M linear code. The same dimension as the original code, but now the elements live in FQ to the M. And if I do this with a GOPA code and Atom code, I have a very nice structure because now all of a sudden the generalized Reed-Solomon code I started with is inside. And not only is this one inside, but all generalized Reed-Solomon code which are of this form were actually we raised actually the X, the support elements by some Frobenius power, and the Y's by some Frobenius power also. So it has a very, if you take a GOPA code, an Atom code, if you take a dual code and extend it to the higher field, it has this very specific structure, very clean, very specific structure. And it sees actually now the X subice and Y subice. The problem is it's a subcode, and you had to find the right subcode. However, there is one thing which also happens because that the generalized Reed-Solomon code is now inside my code that I can compute. There are elements which satisfy unusual properties. Look, there is my generalized Reed-Solomon code which is inside the code that I can compute. Now I'm going to choose a very particular one which is the multiplier y sub 1 up to y sub n, which is inside just because it's an evaluation of a constant polynomial multiplied by y sub I. This one is inside. So this is C0. Then I have C1, which is evaluation of the polynomial x. So it's the coordinates of this element here as y sub I, x sub I. And then there's evaluation of polynomial x squared. So what are the coordinates? Y sub I, x sub I squared. Hey, wait a second, but now I have three elements which have satisfied this equation. The first element by multiplying by the last element should be the middle element squared with respect to a star product. They have it. If you take a random code, you don't have elements like this. Of course, you have an element like this is a zero code word, but non-zero code words, they don't say, you have definitely not this kind of thing going on. So now we are after these elements which satisfy this very peculiar property. So I'm not sure that we found the best way to do this, but this was a way to attack this, is just to try to say, okay, now the problem, I don't know the generalized Reed-Solomon code, but I'm just going to take a basis here of my code that I have, and I'm trying to look at quadratic relations between my basis element. Of course, if I chose the right basis, I have this very nice relation, which is one element of basis multiplied by a second element basis is the square of a third element of my basis. If I don't have the right basis, I don't have this. But forget for one moment about this and just look at what quadratic relationships which you could have between elements of a basis. Of course, this defines a linear code here, which is this one. So just actually the spaces here, the subspaces of quadratic relationships that you have between basis elements. Okay? So this defines, of course, in a natural way, a quadratic form associated to this. You can take the polar form from this. And basically here, this polar form is associated to the Cij here by something which is at the bottom here of the slide, the M sub ij here, given here at the bottom. Good. So far, so good. What's going on if I have the right basis? How do these matrices look like? Well, in the right basis, the relationship, which are now a quadratic relationship between the basis element, it looked like this. It looks like a quadratic form, which has only, you know, a very, almost only zeros, with the only exception of what is going on here at the top. And it's a matrix of rank 3. In characteristic 2, because here the -2 vanishes, you get even something which is of smaller rank 2. I'm going to say, okay, but this is going on if I have a right basis. I don't have the right basis, what are you going to do? Wait a second, there's an invariant here. If you don't have the right basis, it turns out that this quadratic form here, the congruent here, if I don't I choose another basis, actually you go from the matrix space in some basis A to the matrix code of relationship to another basis here B, just by multiplying by an invertible matrix on the left and the transpose on the right. So there's an invariant associated to this, the rank. So what could you do? You have this code. You extend it, this dual code, you extend it, you compute now this quadratic space of relationships. You don't have the right basis, but you know that there is a rank 2 or rank 3 matrix in it coming actually from these unusual elements here. And now what do you have? You have a min-rank problem. You have a min-rank problem. There is an additional structure because you have a min-rank problem where the matrices are symmetric in the odd characteristic case and skew symmetric in the characteristic 2 case. And there isn't even an argument, a geometric argument, which tells you if you start with a random code of the same dimension here as the Gopa code, as long as the dimension of the random code you take is bigger than 2/3, there should not be rank 2 or rank 3 matrices in this. So in essence, you have a way to distinguish if you're able actually to find these rank 2 or 3 matrices in this matrix code. So this is what the distinguisher does. Well, it does something slightly different because we don't even actually have to find these matrices. We can look at an algebraic way of solving this system, trying to find that there's a very good actually now algorithm, algebraic algorithm for solving the min-rank problem. We could use them and trying to see if there's a difference if I start with a min-rank problem associated to a random code or to my Gopa code. And there is. There is. So there's one way of doing this, which is probably not the most efficient way of doing this, but we could analyze it. So it's a particular way here of modeling the fact that a skew matrix here is of rank 2, is just to say that all principal minors of size 4 are 0. Okay? This looks suboptimal. It's not, actually, for some reasons. And the principal minors actually are polynomials of degree 4, but I have a square of a polynomial called the Pfaffian. And so it's you have actually equation of degree 2 instead of 4. So you have a polynomial system expressing that a matrix should be of rank less than 2 here. And then we also have a linear equation coming from the fact that you have a subspace, of course, of these matrices, of this quadratic relationship, which are associated to the code you are interested in. And you can try to solve it. We don't even do this. What we did, actually, we tried to predict what's going on if you apply this Grobner basis techniques actually to this modeling if you start with a random code and a Gopa code or a lanternal code. And there is a difference. The difference, when do you see it and how do you see it? So what do you do? Basically, you have degree 1 equation, degree 2 equations. So first of all, you try to find new degree 2 equations by multiplying all degree 1 equations by monomials here, all possible monomials of degree 1 to get degree 2 equations. Then you perform linear, you want to find the dimension here of this subspace here of equations, gives you some dimension here. So it's basically, it amounts here to find the degree here of the ideal restricted at degree D here, because the things are homogeneous. And you can subtract here the number of this dimension here to the number of monomials. This is actually the Hilbert series here, and so you can compute it. So degree 2 is a polynomial here. You see it directly here. Degree 3 is still polynomial, but a higher degree, of course. You have more monomials. But it can compute it in time, which is basically polynomial as long as D is constant. And you can. Is there a difference between a random system here, what's going on for a random code here, and a GOPA code? Yes. Because there are solutions in the GOPA case. You know them. They exist. In the random case, they are not. And because of this, actually, it's going on that the Hilbert series that you have, a GOPA code, is never 0. And at some point, we can predict, because we can understand very well actually what's going on, it can predict that it's 0 for a random system. And so this gives you the distinguisher. And so do we have to go to a high degree? Well, it turns out that the degree that you have to go here is basically sublinear when the codimension is sublinear, is even actually constant when the codimension, as in the old distinguisher case, is a square root here of length. So it gives you a way, actually, rather efficient to distinguish a GOPA code from a random code. And it also turns out that the Hilbert series as degree 1 is just the dimension here of a usual linear system. Actually, it's precisely the old distinguisher. So it really generalizes what's going on. But we can go beyond, actually, the old distinguisher. That's the nice thing. Here I give an example of parameters of codes which are not distinguishable in the old sense. If you look at degree 1, what's going on? You go at degree 2 here. In the Hilbert series, you see a difference. In the random code, it's 0 here for length 77, but it's not 0 for an Alton code and not for a GOPA code. When I say Alton code, it's generic Alton code, and GOPA code is a GOPA code, of course, but Alton code is a generic Alton code. In the particular case where Alton code is a GOPA code, you have something bigger. So it already sees a difference. And actually, the distinguisher is a slightly better here in the GOPA case because, you know, length 75, you are not able to distinguish a random code from an Alton code, but you can distinguish the GOPA code here because it's a dimension of 80. Okay, so this just to give you a flavor of a distinguisher. Actually, it turns out that you also have an attack here. I'm not going into details into this. So the attack works in a very specific regime. And basically, now it doesn't exploit that you have low-rank matrices in the space, in this matrix space, but it exploits that in the right basis, actually, my matrices of relationship, they have a very, very specific case. They have a block diagonal structure. And if you look at rank defective matrices in it, it should happen when one of these blocks here is rank defective. And if the defect of rank is just 1, actually, it's just one block which is affected by this. And this is basically used in the attack. But I'm not going into detail in the attack. So there's a way to exploit this in a completely different way. And so this gives actually these two completely different attacks. So basically now I'm going to conclude. So what I presented here, you're going to say, OK, look, it gives you a galactic algorithm in case of classic McEliece. It's even not an attack, it's a distinguisher. Right. However, few things. What we did here, I think, should be seen as first step. We really looked at what we could do when we were able to analyze what's going on in the algebraic system. Second thing, we used actually, you know, just the fact that we have elements here which satisfy this equation. I think the equation which is here. So we have elements which behave, but we look just for a pair of a triple of elements of this kind. Actually, you have a bunch of them, and they all have very, you have a bunch of them, and they all go together with some very specific relations. If you go, you take an element y times x sub cubed, actually, they satisfy some property, but, there are relationship between them. So this is not definitely something we don't exploit right now. There's much more structure here in what's going on in the general physical code, but we have just been used right now. But I think that this thing, I mean, it's not the fact that McEliece has resisted all attacks for 55 years, but it's not a coincidence. It's a difficult problem for sure. And if you want to attack a difficult problem, you don't want to attack the difficult problem directly. You are first going actually to attack the difficult problem by looking problems which looks easier. So what looks easier is just trying to attack the McEliece crypto system in, let's say, the regime where the codimension of the code is sublinear. For this, of course, this distinguisher has a sub-exponential complexity, which is better than known attacks. And I'm pretty sure that it can be turned into an attack. It has been difficult to turn the previous distinguisher into an attack because, in this case, the Grobner basis approach did not give you directly a way to solve the system. Now we have, we can solve the system here at the degree where we see actually that it should be 0 for a random case. We have actually a way to solve the system, and probably to understand what's going on. I mean, the only problem right now is that you have many solutions. So you probably have to choose actually the right solution in this. But I think this is not a problem which is not doable. So this is probably something that can be done. So I'm pessimistic about the security of the McEliece crypto system. In the sublinear regime, I really believe actually that there's something going on here just because of distinguisher. I also believe what I said here about the distinguisher is just, attack 1.0, really. Even attack 0.0 here. Because I think what we have now is really a way to distinguish codes up to, regimes where we were unable to do anything. So this was something, what we could not do for a long time. Now we are able to do this. So I really think actually this will lead to a new thing on attack. I think if there is now a way to challenge the McEliece crypto system, and not to attack it, I'm not sure, it's going to be concrete attacks at the end of the day, but this kind of work actually might be a way to go. Something that I haven't seen for years actually, which we see right now. There is also something to do which is probably, I don't know if it's complicated or not, but it's really to understand actually the distinguisher. Right now it's in terms of Grobner basis, and we really want to explain this in terms of code objects. So what happened for the old distinguisher when we were able to have a description of it as a square product here, it gives us a good way actually to understand it. And it's probably something which is needed actually for this distinguisher. So you get away actually from this Grobner basis stuff and try to explain everything in terms of codes. And in general, I think this is the general methodology which is used here. So forget about trying to solve the McEliece crypto system problem itself directly. It's a hard problem, maybe not, maybe I'm wrong, but I think it has chances to be really hard. But there is really now a way actually to attack this, and I finish with this.
Yeah, we have time for 1 or 2 questions. So if you take the mic, either of them. Okay, then I will ask a question. So, could you say something about the status regarding security for the CFS signature scheme?
Good question. If I believe it will be attacked, yes. If this thing attacks it, no. The problem for the CFS scheme is really the fact that this square product, which are a consideration which allowed us to decrease the degree, but it just doesn't work. It just doesn't work. So this is the first problem. Now you could say, okay, could you attack it by just looking for degree 2 matrices in this code space? Maybe yes. This is something which might be doable, but for this, actually, you have to solve the problem of really understanding the space of solutions here in this algebraic system. Once we understand actually the set of solutions of the whole algebraic system that we have set up here, well, the CFS scheme might be broken.
Have any further questions, then let's thank Jean-Pierre